Welcome to our exploration of clocks in strong gravitational fields, where we ask a simple yet profound question: how does gravity change the passage of time? Over the next slides, we'll connect thought experiments, landmark tests, and modern technology to show how gravity literally slows clocks and why that effect matters from laboratories to satellites and even everyday devices. Einstein's equivalence principle tells us that being stationary in a gravitational field is locally indistinguishable from accelerating in flat space, and the classic light-o'clock thought experiment makes the consequence clear. If an accelerating light clock runs slow, then a clock held fixed in gravity must also run slow, establishing gravitational time dilation as a universal, physical phenomenon. The Pound-Rebka experiment gave the first terrestrial confirmation of gravitational redshift by sending gamma rays up a 22-meter tower at Harvard and measuring a tiny frequency shift at the detector, matching Einstein's prediction to within 1%, and providing direct experimental evidence that clocks deeper in gravity run slower than those higher up. In 1971, the Hafele-Keating experiment flew cesium atomic clocks east and west around the world and compared them to ground references, applying velocity corrections and finding remaining discrepancies of tens of nanoseconds. The combined results agreed with relativity, demonstrating that both kinematic and gravitational time dilation produce effects large enough to observe on human timescales. The hydrogen maser experiments push this further by flying a highly stable hydrogen maser to about 10,000 kilometers and continuously comparing it to ground clocks by radio, observing the predicted time shift of about plus 0.45 microseconds per orbit and confirming general relativity and the Schwarzschild prediction to parts in 10,000, validating theory with precision measurements. Modern optical lattice clocks and the NIST 2010 aluminum Moyen tests show that time dilation is detectable at everyday scales. Optical clocks can resolve a 1-foot elevation difference, and the NIST experiment measured a 33-centimeter offset, where the upper clock ran about 0.3 nanoseconds per day faster, proving the effect matters even in small, practical geometries. GPS satellites illustrate why relativistic corrections are essential. Atomic clocks in orbit gain roughly plus 45 microseconds per day compared to ground clocks because of weaker gravity, and firmware must continually subtract about 38 microseconds to avoid positioning errors that would otherwise accumulate to kilometers per day, keeping navigation accurate for billions of users. Gravitational time dilation touches daily life in subtle ways. Someone living on the 20th floor experiences slightly weaker gravity and ages by nanoseconds more per year than someone at street level. A tiny but measurable difference now confirmed by optical clocks, reminding us that general relativity produces real, if imperceptible, consequences across ordinary urban heights. Near a black hole, the effects become extreme. As a clock falls into a deep gravitational potential, distant observers see its ticking slow and redshift until it appears to freeze at the horizon, an observation outcome reflecting that infinite redshift separates external observers from events at the horizon, even though the infalling clock experiences its own local proper time differently. When planning interplanetary systems, we must account for weaker gravity on other worlds. Clocks on the Moon and Mars run faster than Earth, by measurable amounts on the order of tens to hundreds of microseconds per day, so synchronizing navigation, communications, and data logs requires adopting local timescales or offsets, analogous to UTC, to keep multi-time world systems coordinated. Next-generation optical clocks offer unprecedented stability around 10, 19, enabling measurements of time dilation at microscopic scales and across hairy-thin distances, while also opening new tests of fundamental physics. They can probe higher-order relativistic terms, search for interactions beyond the standard model, and map tiny variations of gravitational fields inside materials. The journey from laboratory to wrist is already underway as atomic timekeeping shrinks toward cubic crucentimeter devices and wearable sensors. Future watches could log altitude history by monitoring tiny changes in their tick rate turning Einstein's abstract prediction into a personalized gravity log that tracks how elevation and environment subtly shape each person's passage of time.